Hi, everybody. I'm Chris Tisdell. Thank you for watching my conference presentation. Let me share my slides with you and we can get going. Okay, so the title of this presentation is the precise number of solutions to fractional boundary value problems using shooting methods. And it's joint work with Saleh and Jagan and Chris. And I'm coming to you all the way from Australia today. So what do you know about Australia? Do you know anything? Have you been here? One thing that I think we're quite famous for is strange animals. So most of them are friendly, but we have a whole bunch of very, very strange animals called marsupials. Here's a picture of Sydney from the air. Sydney is the capital of New South Wales, which is a state and former colony in Australia. And here's some of our neighbours. If you look down the bottom, this is our main campus. It's in the eastern suburbs of Sydney. You've got downtown over here. You've got Sydney Harbour. You've got beaches to the east. And it's quite a large university by Australian standards. It's got about 60 or 70,000 students. So I would invite you all to come and visit me in Sydney. Sydney's an amazing city. It's lots of interesting things happening. It's very safe. There's some very good universities here. So please come and say hello. All right, so on to the presentation. I think it's fair to say that as mathematicians and engineers, scientists, we love to count. And we count whenever we can. And the science of counting and ways of counting is what we do, okay, a lot of the time. And a very common question here is, suppose you've got an equation. Is there one solution, no solutions, more than one solution? And if there's more than one solution, then how many? So these are sort of ancient questions and some of the questions I'll be looking at today in this presentation. So the boundary value problem that we're going to look at is contained here. Y is a vector valued function, so is f. Q, the order of the differential equation, is between 0 and 1. And these are the boundary conditions. You can see that they're multi-point boundary conditions. The coefficients are matrices. We assume that that the first coefficient is invertible. And so the question is, how can we count the number of solutions to this problem? And we're going to use shooting methods, and shooting methods are well known for ordinary differential equations, but they haven't really been discussed much for fractional problems. Okay, so that's sort of the gap or the challenge that this research is looking to address. All right, so I'll show you the main theorem. So suppose A0 is invertible, F's continuous, and Lipschitz in the sense that this inequality holds. And let S be a parameter. All right, well, we switch our attention to the initial value problem associated with our boundary value problem, and you let V be a solution. So if V is the unique solution, the conclusion of our main theorem is the following. The fractional boundary value problem has the same number of solutions as there are distinct roots to this problem here. So basically, you set this equal to 0 and you count the number of solutions. If this equation 6 has 3 solutions, then our original boundary value problem will also have 3 solutions. If equation 6 has 1 solution, then the boundary value problem has 1 solution. If there's no solutions, then the boundary value problem has no solutions. So that's sort of how it works. But let's discuss a couple of examples, and you'll see, how to apply it. So let's have a look at a really simple scalar valued non-linear fractional problem here. Okay, you've got 3 points. You've got you're just working in with scalar valued functions here. The right hand side is continuous and Lipschitz because it has a bounded partial derivative with respect to p. And so it's Lipschitz, so it satisfies the first condition of our main theorem. And what this means is when we switch our attention to the initial value problem, this has a unique solution. Okay, F's Lipschitz and continuous means that 11, 12 has to have a unique solution. So all the conditions of our theorem are satisfied, and so we now look at this problem. We set it equal to 0, and we look at this problem. And then we can conclude that 9 and 10 have the same number of solutions as there are solutions to this problem. Yeah. Okay, now we don't know how to compute the exact number of solutions, but we have this relationship at the moment. So let me show you another one. The results in our main theorem are also new for the case Q equals 1 when you've got multiple point boundary conditions. Now here we've got a nonlinear term as well. We can still get it to work. Okay, so let me show you how. So K is a constant in this problem. We switch over to the initial value problem, and luckily we can solve it explicitly. It's only got one solution. So this is our solution to the IVP. Yeah. And then we can sub this into our equation of interest. This is our old H equals 0 type equation. I've used phi over here. So now the question is, how many solutions does this equation have? Okay, so well, it depends on K, I guess, but for K between 0 and 10, this function phi, it looks something like that, okay? And I haven't drawn it exactly, but there's one solution that's to the left of -1, and there's one solution to the right of -1. So there's exactly 2 solutions to this problem. That means the original problem has exactly 2 solutions. Okay, so they're my basic results and some examples. You can replace this Lipschitz condition with the assumption that all the solutions to initial value problems are unique. Okay, and that's really what you want with these kind of problems. Okay, and the Lipschitz condition just guarantees that. All right, so the results are new for the fractional case. They're new for the case involves more than 2 points. They're new for ODEs in the multi-point situation, and when you've got some non-linear term in there. All right, everybody, I hope you enjoyed this presentation. Best wishes from Sydney and New South Wales, Australia. I hope you get to come out here one day. Once again, please, if you want to visit, please come and visit, and enjoy the conference. And I'll say goodbye. Thanks, everybody. Bye.